Hi, in this video we are showing you how we can analyze GSM signals or 2G signals with the IDA2 from Narda. Right now we're located in Europe and we're looking at the spectrum from 800 MHz to the stop frequency 2 GHz. And we can see some GSM 900 signals here in the spectrum and the waterfall, and also some lower or weaker signals, GSM 1800 up here. So what I typically like to do is I just switch on our video filter so that we can smooth the spectrum trace and better see what's going on in spectrum. And as we have so strong signals right here now in the GSM 900 area, we're focusing on these signals only. So let's adjust our upper frequency boundary to 1 GHz. We can do this when clicking here, f-stop, and then go to 1 GHz. As we see now some downlink signals in this area. We also see a couple of uplink signals right here. But as the downlink signals are so much stronger and as they are there all the time, we now focus on this area here by activating a start frequency that starts with 1920 MHz. And also we can adjust our upper frequency boundary again, and we have that and set it to 9060 MHz by going to f-stop and type in 960 MHz. So now we can see plenty of signals, and also in this case again we can increase or enhance the view onto these signals by adjusting the bandwidth settings. Right now our RBW amounts to 300 kHz. By adjusting that RBW to, let's say, 50 kHz, we can of course see a much lower noise floor, and we also see the signals in the spectrum and the spectrogram much clearer. Of course, as we have a lower RBW, also our sweep time may increase. So now we see some channels which are switched on all the time, others are switched on not all the time, they are more or less pulsed. So this is the main differentiator between the broadcast channels switched on all the time and the traffic channels switched on only when it's necessary. In the next step we'll focus on one of these broadcast channels and analyze it also in time domain. So what we do next is we type the Spectrogram Marker button, and we move now the marker to one of these broadcast channels here. I have already pre-selected one. I could also go to highest peak or some other marker function, and as next step I will move that marker with its center frequency to the center. And afterwards I will focus on that very center frequency. So by typing escape, I will now switch off the marker again, and by changing with a double click from f-start, f-stop to f-send, f-span, I can now decrease the span and by that focus on that selected or pre-selected broadcast channel. So let's do this once again, and let's select a final frequency span of 5 MHz. I can now see this broadcast channel very nicely. What I can also do, I analyze this signal only in spectrum. And in the spectrum I can also activate different traces, such as the maximum trace and the minimum trace. And this trace configuration is now very useful because it shows us that even a broadcast channel which is switched on all the time has a specific behavior. So what we can see is that the max trace covers the entire band, and that the minimum trace is slightly shifted to the right, which indicates that there is still in some phases a portion which is switched off, or a portion in the band that is only focusing on the right frequency shift part. And we will take a closer look at this in the next step, or in the second next step. But first, let's take a look at how this signal looks like in time domain. So what we can do now is we click on extras, and with help of this function, we can now use all the other modes inside the IDA too, if available, and analyze the signal, for example, in time domain, which is similar to an oscilloscope view. So now we have the same center frequency, and we also have a specific channel bandwidth. And what we basically see is that this signal changes in a specific way. As you see, as I was just showing more or less, you see that the trace of that oscilloscope view and its quality may change whether you have precisely tuned into the channel frequency or the center frequency. And when it's about GSM, you should typically know that you always have to think in 200 kilohertz bands. So I just wanted to make sure that I'm more or less right in the center of that frequency band of interest. And when now looking at these signals here, we can see pretty nicely these are the Gsm time slots. They, when you take a closer look in this GSM standard, last approximately 577 microseconds. And what we can also see is that you have some time slots that have a higher peak or a higher level than others. So in this channel, power saving mode is already activated. This is a matter of the operator's usage. And sometimes we even see some old edge pulses popping up. Edge is making use of a phase shift keying, whereas typical GSM is making use of frequency shift keying, or actually GMSK. And well, you can basically differentiate those two different modulation schemes in time domain based on how the time slots look like. And I'll now just try to catch some slots or some frames that contain both GMSK and PSK modulation schemes. So just by pressing that hold button, I sometimes am able to do so. In this case, not always. Well, now right here we can see, for example, one edge pulse. And what we also see is a very smooth pulse right here, which is actually the frequency correction burst. And in order to analyze that frequency correction burst further, we will now make use of another operating mode within the IDA, by clicking once again to extras and go to the IQ analyzer. And now we have to adjust the bandwidth, increase it up to several megahertz. In this case, now we're taking a bandwidth of, or a frequency span of 10.67 megahertz. Within this mode, we have different subviews. For example, the high resolution spectrogram full. And what this mode typically does, it first collects a huge amount of data and then reprocesses these data again and again until we can provide a very detailed view onto the signal. So what we can see now is not a usual spectrogram that changes in the dimension of seconds, but we can actually see what's going on from millisecond to millisecond. And now let me just wait again for the next useful moment, and then we can actually highlight. Right now we have captured one, and now we can highlight what the frequency correction burst actually means. So this is the moment of the frequency correction burst that appears every 10th time frame, so every approximately 46 milliseconds. and it consists of a signal which is not switched off, but it's actually a non-modulated phase where only the carrier is shifted for the length of one time slot to the right or to the higher frequency. We can actually enhance this view by changing from the high-resolution spectrogram full to the high-resolution spectrogram zoom. And now we can scroll down and make even more use of that captured time span that amounts to 18.75 milliseconds. And now we can again see what the frequency correction burst actually means. So there are a couple of more means how to analyze GSM in detail. And one of these views is also the persistence spectrum that shows us by colors whether specific channels are more occupied or less occupied. And once again, the broadcast channels here, they have a more red colored depiction, whereas the traffic channels, which appear in a pulsed way, are not as red, or they're rather blue or green marked. All right, that's it so far. This is one mean, or a couple of means, how to analyze GSM with help of the IDA 2 from Narda. Thanks for attending.